right, today we are tackling an absolute giant. This is the book for a lot of people when it comes to understanding the entire field of artificial intelligence. We're going to break down the core ideas from Stuart Russell and Peter Norvig's Artificial Intelligence, a Modern Approach. So let's just dive right in.
Hello, and welcome to LM Reads. I'm a researcher who loves to break down fascinating books for you.
It's a term we hear every single day. But what does it actually mean? Is it about building a machine that can fool us into thinking it's human? Or maybe one that can reason with perfect cold logic? Or is it something else entirely? So here's our roadmap. We're going to follow the book structure pretty closely. We'll start with defining AI. Then we'll meet this idea of agents, see how they solve problems, how they deal with uncertainty, and finally the really cool part, how they actually learn from data. Okay, first up, what even is AI? The book lays out this awesome idea that researchers have kind of been chasing 4 different goals. It all breaks down along 2 main questions. Are we trying to mimic humans, or are we aiming for perfect rationality? And are we focused on the internal, thinking, or just the external, acting? And this framework basically organizes the entire history of the field. You've got these different camps, right? Some try to copy human thinking. Others just want to copy human acting, like the whole Turing test idea. Then you have the other side aiming for pure logical rationality. But the book argues that the most powerful and modern approach is right there in that bottom right box, building agents that don't just think rationally, but act rationally to get the best possible outcome. And honestly, that one idea is the key to everything else we're going to talk about. So let's really get to know this rational agent. It's basically the main character in our story today, and it's the fundamental concept that powers everything from your phone's GPS to the most advanced AI models out there. At its core, an agent is a pretty simple idea. It just perceives the world, a self-driving car uses cameras, a thermostat uses a temperature sensor, and it acts on the world. The car turns the wheel, the thermostat kicks on the heat. The rational part, though, that's crucial. It means it's not just acting randomly, it's always trying to act to get the best possible result. But that begs a big question, right? How does an agent even know what the best result is? Well, that's where something called a utility function comes in. Think of it like the agent's internal scorecard, its personal definition of success. For a chess AI, utility is simple: win the game. For a delivery drone, it's probably a mix of speed and safety. A rational agent is simply a utility maximizer. It always chooses the action it believes will lead to the highest score according to that function. Okay, so we've got a rational agent, and it wants to maximize its utility. Great. How does it figure out what to do? Well, let's start with the simplest case, a world where the agent knows everything, and the results of its actions are totally certain. The book uses this fantastic, classic example that you've probably used 1,000 times, just getting directions between 2 cities. This isn't just a navigation problem. At its heart, it is a foundational AI search problem. So to solve this, the agent first has to frame the problem. The possible states are just all the cities it could be in. The possible actions are driving on the roads that connect them. And the goal? Well, that's simple. Get to the state we call Bucharest. This map illustrates the idea perfectly. Imagine this whole map of Romania is just a giant network. The agent's starting point, its initial state, is arid, and its goal state is Bucharest. The map itself is what we call the search space, and the agent's whole job is to find the best path through it. So how does it do this without taking forever? It uses a heuristic, which is just a fancy word for a smart rule of thumb. For navigation, a great heuristic is to always check out the path towards the city that's closest to your final destination as the crow flies. By using this little shortcut, the agent can intelligently search the most promising routes first instead of just trying every single road randomly. But search isn't just for maps. It's also incredibly powerful for any problem that you can define with a set of hard rules or constraints. A perfect example is solving a Sudoku puzzle. Think about it. Each empty square is a variable. The possible values for each variable are the digits 1 through 9, and the constraints are just the rules of the game. No digit can show up twice in the same row, column, or 3x3 box. A CSP solver then uses search to find a number for every square that satisfies all those rules. All right, so far we've been hanging out in this perfect, predictable world. But what happens when we move into the real world, which, as we all know, is messy, uncertain, and incomplete? Well, that's the next big challenge for AI. I mean, what if you're a doctor trying to diagnose a patient or a detective trying to solve a crime? You never have all the facts. You have clues, you have symptoms, and you have probabilities. You can't just use simple search anymore. You have to reason under uncertainty. And this is where probability theory becomes absolutely essential for AI. A key tool for this is the Bayesian network. The best way to think of it is as a map of cause and effect. It lets an agent see the relationships between different events, like how a burglary might trigger an alarm, and, most importantly, the probabilities that link them all together. The real power here is that an agent can reason backwards from effects to causes. It can take one little piece of evidence, like your neighbor Mary calls, and use the network to update its belief about the probability of a burglary. It's literally making a smart bet based on the evidence it has. And this brings us to the final, and I think most powerful idea in the book. We've seen how an agent can plan and reason, but the ultimate step is for that agent to actually get better all on its own. This is, of course, where machine learning comes in. Instead of having its utility function and its model of the world hard-coded from the start, a learning agent can figure them out from data. It looks at examples, it finds patterns, and it adjusts its own internal workings to get better over time. It literally gets smarter through experience. And this all comes full circle, right back to the core principle of the entire book. Whether an agent is searching a map, reasoning with probabilities, or learning from data, its North Star is always the same. It's trying to pick the action that will give it the maximum expected utility. This one simple idea unifies the whole field. So, what's the final verdict? Why is this book so essential? Well, because it gives you the complete blueprint. It shows you how search, logic, probability, and learning all fit together under this one unifying idea of rational agents. It takes these super complex theories and grounds them in problems you can actually visualize, like navigating a map or solving a puzzle. If you really want to go beyond the headlines and understand the deep foundations of modern AI, this is where you start. In this explainer, we're going to build an intelligent machine from the ground up. We're going to give it the essential tools it needs, piece by piece, so it can operate out there in the world. So, let's just jump right in with the biggest question of them all, right? When we talk about AI, what are we actually talking about? Is the goal to build a machine that thinks and feels just like a person? Or is intelligence something more practical? Something defined not by what it thinks, but by what it does? You see, the core idea in modern AI has kind of moved away from perfectly mimicking the human mind. The real goal, the North Star, is to build something called a rational agent. And here's our blueprint. A rational agent isn't judged by its internal thoughts, but by its performance. It perceives its environment, and then it acts to maximize its chances of success. It doesn't matter if it's a robot navigating the terrain on Mars or an algorithm playing chess. The goal is always the same: make the optimal move. What's so fascinating is that this isn't some brand new idea that came out of computer science. The concept of tying intelligence directly to action, well, that has deep, deep roots in philosophy, stretching all the way back to Aristotle. Okay, so how do we actually equip our agent to act rationally? Let's start with its very first tool. This one is designed for a world that works like a puzzle, predictable with clear rules. This tool is search. Before our agent can even start to play, it has to understand the rules of the game. I mean, think about any board game. You have to know the starting position, what moves are legal, what happens after each move, what it actually means to win, and how you keep score. This framework lets us turn almost any problem into a solvable game. So this process is a bit like a detective exploring a maze. The frontier is just all the hallways they haven't gone down yet. They pick one, check it out, and if it's not the exit, they add all the new connecting hallways to their to-do list. But, and this is the crucial part, they mark the path they just took as explored. That way they don't waste time going in circles. Now, you can probably see the issue here. Just trying every single path might work eventually, but for any remotely complex problem, it is wildly inefficient. A truly rational agent has to be smarter than that. And this illustrates the difference perfectly. Uninformed search is basically blind. It's just wandering through the maze, checking every single turn. But informed search, it has a heuristic. Think of it like a clue or a compass that's generally pointing toward the exit. It doesn't know the exact path, but it has a smart guess that helps it prioritize which paths to check first, saving a massive amount of time. And this brings us to a huge challenge. Search is fantastic for games like chess, where all the rules are fixed. But the real world, it's messy, it's unpredictable, it is full of incomplete information. Our agent is going to need another tool. So let's grab the second tool for our agent. This one lets it stop thinking in black and white certainties and start thinking in shades of gray. It's the ability to reason using probability. To handle all this uncertainty, our agent uses something called a Bayesian network. The best way to think of it is as a map of cause and effect. Instead of saying a burglary causes an alarm, the network says a burglary increases the probability of an alarm. It's this whole web of connections where each event can influence the likelihood of others. And this table is what powers that whole network. It's a conditional probability table, or CPT, and it's what puts hard numbers on those relationships. For example, it tells the agent that if there's a burglary but no earthquake, there's a 94% chance the alarm will go off. These are the numbers the agent actually uses to reason. And here is where it gets really powerful. When the agent gets new information, say a neighbor calls to say the alarm is ringing, it doesn't just jump to a conclusion. No, it feeds this evidence back into the network to calculate an updated belief, to ask, okay, now what's the new probability that a burglary has occurred? All right, our agent can solve puzzles, and it can reason about uncertainty, but it's still, well, it's static. Its knowledge is fixed. The final tool in its basic kit gives it the power to adapt and actually get smarter over time. This is, quite simply, learning by doing. I mean, think of it just like training a puppy. You don't give it a rule book, right? You reward it for good behavior and you discourage bad behavior. Reinforcement learning works on that exact same principle of trial and error. This simple feedback loop is the engine of learning. The agent takes an action, it gets a response from the world, and it uses that response to tweak its internal strategy. Over thousands or even millions of cycles, this process lets an AI master incredibly complex tasks, from video games to robotic control. A positive reward, that +1, it's like a digital pat on the head. It strengthens the connection between an action and a good outcome. It basically teaches the agent, hey, what you just did in that situation, great idea. Let's do that more often. And on the other hand, a negative reward, the -1, that serves as a course correction. It weakens the link between an action and a bad outcome, teaching the agent an equally valuable lesson. Okay, let's maybe not try that again. Okay, so let's step back and look at what we've assembled. We've given our agent a complete foundational toolkit for intelligent action. And these three capabilities right here, they are the pillars of modern AI. You have the ability to plan and solve puzzles through search, the ability to reason about a messy, uncertain world using probability, and the ability to get better over time through learning. And this brilliant combination isn't just theoretical. It is the engine behind some of the most impressive achievements in AI history, from world champion game-playing machines like Deep Blue to autonomous robots exploring other planets. And that brings us to the most exciting part. This is all just the beginning. This toolkit, the ability to search, to reason, and to learn, is the foundation. And as these tools get more powerful and combine in new ways, the possibilities for what rational agents can achieve, well, they become almost limitless. Which leaves us with the ultimate question. What are we going to build next?
We're going to go on a quest to figure out what it really means for a machine to be intelligent. And we're going to uncover this one single really powerful idea that drives so much of modern AI. So let's kick things off with the one question that started this entire field.
This is it. This is the question that started the whole shebang. For decades, this has been the holy grail for computer scientists, for philosophers, for everyone. And, it sounds like a simple question, right? But to even start to answer it, we have to ask something even bigger. What is intelligence, anyway? Okay, so our first step is to try and define intelligence. And to really get where we are now, which is all about optimization, we have to go back to the beginning. Back when the goal wasn't to be perfect, but just to be a really, really good copycat. And that brings us to the famous Turing test, cooked up by Alan Turing way back in 1950. For the longest time, this was the benchmark. The whole idea was pretty simple. If a machine can fool a person into thinking it's also a person, well, then it must be intelligent. It's the ultimate imitation game. But here's where the story gets really interesting. The goal of AI, it started to shift. It went from just acting humanly to something way more powerful, acting rationally. I mean, think about it. Why just imitate a person with all of our weird biases and mistakes? The real prize is to create something that does the right thing, an agent that acts optimally to get the best possible result. And that little shift from imitation to optimization, that is the one idea that truly defines modern AI.
And this shift brings us to the hero of our story today, the rational agent. This is the big concept, the building block that underpins everything from a chess-playing supercomputer to a self-driving car.
So, what is a rational agent? Well, simply put, it's something that looks at its environment and takes actions to maximize its chance of success. It all comes down to this idea of utility, which is really just a score for how good an outcome is. A rational agent is just trying to get the highest score possible. It's not about feeling, it's not about thinking like us, it is all about optimizing.
Okay, that sounds great in theory. But let's be real, the world is messy, it's uncertain, and it is filled with a mind-boggling number of choices. So how does our rational agent hero actually sort through all of this complexity to make the best decision?
Well, the first big challenge is just finding a path forward. When you have countless possibilities, an agent needs a smart way to search for the best route without just getting totally lost in a noise.
Let's make this super concrete with a classic AI problem, finding the shortest way to drive across a country. We need to get from a city called Arad to another one, Bucharest. What's the best way to go?
To figure this out, the agent has to look at the entire problem space. Just picture a map with every single possible route, every city, every road. Trying to explore all of them one by one, that would be impossibly slow. It's like trying every single path in a giant maze. The agent needs a smarter way to search. It needs a shortcut.
And that shortcut has a name. It's called a heuristic. You can think of it as an educated guess or a clever rule of thumb. It helps the agent prioritize which paths look the most promising so it can check those out first. And this saves a massive, massive amount of time.
So for our driving problem, a brilliant heuristic is just the straight line distance to the destination, as the crow flies. Now, that's not the actual driving distance, of course, but it's a fantastic clue. An agent using this heuristic will always check out the city that's geographically closest to Bucharest first. It is a simple, elegant shortcut that makes a ridiculously huge problem totally manageable.
Okay, so search and heuristics help an agent find a path in a world it knows, like a map. But what happens when the world is uncertain? What does an agent do when it doesn't have all the facts? And that's the thing, isn't it? The real world isn't some neat and tidy map. It is full of maybes and probablys and what-ifs. So a truly rational agent can't rely on being 100% certain. It has to think in terms of probabilities.
And the tool for that job is called a Bayesian network. This is a really powerful way to map out cause and effect in a fuzzy, uncertain world. It lets an agent intelligently update what it believes as new evidence rolls in.
Let me walk you through a classic example to show you how this works. Okay, picture this. You have a burglar alarm. It can be set off by a burglar or, much less likely, by an earthquake. Now, your neighbors, John and Mary, they promise to call you if they hear it go off. So if John calls, your belief that there was a burglary goes way, way up. But then, you hear on the news there was a little earthquake nearby. Suddenly, the alarm is explained away. Your belief in a burglary plummets. This is the kind of sophisticated, probabilistic reasoning a Bayesian network lets an agent do. So, now we have an agent that can search for solutions and reason when things are uncertain. Now let's see these ideas collide in one of the most famous showdowns in the entire history of artificial intelligence.
We're going to May 11th, 1997. It's the deciding game between the world chess champion, the legendary Garry Kasparov, and IBM's supercomputer, Deep Blue. After a stunning move by the machine, Kasparov resigned. For the first time ever, a machine had beaten the reigning world champion in a classical match. The question on everyone's mind was, how on earth did it do it?
It did it by using the exact framework we've been talking about. First, Deep Blue evaluated the board. It had a utility function, a way to give a score to any position. Second, it used incredibly powerful search algorithms to explore this huge tree of possible future moves. It was searching for the best route, just like our trip across Romania, but on an absolutely astronomical scale. And third, it picked the move that led to the part of that tree with the highest expected utility, the highest score.
So you see, Deep Blue wasn't thinking like a human. It wasn't imitating Kasparov. It was a rational agent, pure and simple. It combined a utility score with a massive search, guided by clever heuristics, to find the mathematically best move. This was the rational agent framework in glorious, world-beating action.
And look, this is not just about board games. This rational agent model, defining a goal, searching for a solution, and optimizing for the best outcome, this is the foundation for so much of the AI we see all around us today. It's in the robots that build cars, it's in the algorithms that plan shipping routes around the globe, and it's even in systems that are helping doctors diagnose diseases. Which, of course, brings us to our final, lingering question. An agent that maximizes its utility will always act rationally based on how it's programmed. But that leaves the biggest and maybe the hardest challenge of all up to us, the creators. How do we define what is truly useful? And that, perhaps, is the next great quest for the field of AI. Let me know in the comments if this makes you want to pick up the book.